In this segment, I'm going to talk about photoelectron spectroscopy, which is an experimental technique which is not actually described in the textbook, but I think of it as a good way to explain why we think about the electronic structure of atoms the way we do. Okay, so I'll try to use this video to convey some of those ideas to you in what I hope is the simplest way I can manage. So photoelectron spectroscopy is a way to learn about how electrons are arranged into atoms. Essentially, it's sort of analogous to what you might do with a mechanical object. If I gave you a somewhat complicated mechanical object and asked you to figure out how it worked and what it did, there's a reasonable chance that a number of you might decide that a way to try and sort that out would be to take it apart. Right? See how the different pieces fit together, what did they do, how did they interact. That's kind of what's going to happen here. So in photoelectron spectroscopy, we're going to actually knock electrons off of our atom and use that as a way to figure out how tightly bound the different electrons are. Okay, it's a lot like the photoelectric effect, as it says here, right? So the experiment is very similar to the photoelectric effect, except that now instead of having a piece of metal as the target I'm going to shoot light at, I want to use an individual gas phase atom or a free atom. Okay, that does make the experiment harder, not by as much as it might sound, but it does make it harder to do the experiment when I want to just have my light interacting with individual atoms rather than with a bulk piece of metal. Okay. In order to do this, I want to be able to knock the electrons out of the atom no matter how tightly bound they are. So what I want to do is I want to use high energy photons out in the ultraviolet or maybe even the X-ray part of the spectrum. So I'm going to go for some very short wavelength photons here. So I have enough energy to knock out even a tightly bound electron. Okay. Just like in the photoelectric effect, we can look for the ejected electrons and we can measure their kinetic energies and use that information to figure out how tightly bound those electrons were before they got removed. Okay, so let's take a quick look at how we would do the experiment. This is a picture that's similar to one I showed you before when I was talking about how to measure the speeds of gas molecules, right? So again, I have this source that sprays the gas out and gets me just this stream of molecules here flowing that way, okay? This is all in a vacuum chamber and it's at a low enough pressure that those molecules, as they're moving across my screen, they're not colliding with anything, okay? That means individually, one at a time, I just have one atom that might be in the site of my, my light source. My light source, some sort of laser or what have you that produces these high energy photons, comes across perpendicular to that. We have this interaction region here. That's where the actual interaction between the light, the photons, and the atoms will take place. And then I would put my detector to try and count up the electrons. It would probably be perpendicular to both of those. So it would be in the plane like in front of the screen, something like that, okay? The first atom I'm going to start with is hydrogen. So I'll also point out that if I wanted to do this experiment with hydrogen, I want hydrogen atoms in my stream of gas and not hydrogen molecules. To do that, what I would have to do is I would have to put some high voltage electrodes across here, so that right as the molecules were coming out of there, they had to fly through a region where there was a very high voltage, right? Sort of like when I did the emission spectrum video, I talked about having the power supply that had this 5,000 volts across there. I'd do something like that. I'd put just 2 electrodes there, so as the hydrogen molecules emerged, they had to fly through that strong electric field. The energy there would be enough to actually be able to separate the atoms apart. So I just have a little discharge going across there that broke my hydrogen molecules down into atoms. So I do this with a hydrogen atom. A hydrogen atom only has 1 electron, right? So we would expect that the binding energy, the amount of force it takes to pull the electron off of a hydrogen atom should always be the same. There's no reason why we would think that one hydrogen atom should be different from another. And sure enough, if I do this with hydrogen atoms, all the electrons I detect have the same kinetic energy, okay? This says if I do this experiment using a wavelength of 10.06 nanometers, my electrons come out and they've got this kinetic energy, but it's in some wild units, okay? It's in megajoules, that's 10 to the 6th, so megajoules per mole. Okay, that means 10.6 million joules. That would be the total energy if I had 1 mole of these ejected electrons. So Avogadro's number of electrons altogether would add up to that. I want to find the electron binding energy from those numbers. So let's give that a try, okay? The first thing I'm going to do is, I guess I'm going to do this starting from the photon wavelength, okay? So I'm going to start with my 10.06 nanometers, and I'm going to turn that into an energy. Remember our energy equation said E is equal to h nu, and that's also equal to hc over lambda, which is the form I'm going to use here since what I have is a wavelength, okay? H is 6.626 times 10 to the minus 34th power. That's in joules seconds. Speed of light I'm putting in is 3 times 10 to the 8th. That's in meters per second. Again, it's very, very close to 3. It's not exactly 3, but that'll work for us. Then my wavelength is 10.06, but it's in nanometers, so I'm going to do what I always do and just put that in and say times 10 to the minus 9, which will make it into meters. It looks a little funny down there, but it does work, okay? When I do this, I get 1.98 times 10 to the minus 17, according to my notes, and my surviving unit is joules. That should strike you as a large photon energy, right? The ones we've seen prior to this have been around 10 to the minus 19 joules, but now my wavelength here is just 10 nanometers, right? So before I've been in hundreds of nanometers, so I have changed the wavelength by quite a bit. Makes sense that as the wavelength gets short, my energy should be larger, okay? There's one more thing I have to do with that. Because my number here is in joules per mole or megajoules per mole, I'm going to next take that photon energy and I'm going to convert it from joules for 1 photon to joules per mole, okay? So let me do that. I just calculated on the previous one that I had 1.98 times 10 to the minus 17 joules. That's what's equal to 1 photon. Okay, I want to see what I get per mole of photons. So if I take that thing and imagine writing it maybe as 1.98, hang on a minute, I'm doing it backwards, aren't I? No. 1.98 times 10 to the minus 17 joules. I'm going to write it as joules per photon because it was joules for 1 photon after all, right? I'm going to say I'm going to multiply that by a piece, which is Avogadro's number, in this case photons, per mole. And then photons effectively is a unit that I can cancel from here, okay? If I do that, what I get, according to my notes, is 1.19 times 10 to the 7th. That's in joules per mole. And that in turn would give me 11.9 megajoules per mole, because a megajoule is 10 to the 6th joules after all, okay? So that's my photon energy in these megajoule per mole units, all right? I could have, if I wanted to, I could have taken this thing, I guess, and changed that to get it out of moles and into being for 1 atom, but I happen to have gone this way, okay? A mole of photons shouldn't bother you, right? A mole of anything is just Avogadro's number of them. So here, when I wanted to get from 1 to a mole, what did I do? I multiplied by Avogadro's number. Same thing as you would do if it was a mole of atoms, mole of anything else, right? There's no reason I can't have a mole of photons. So now I'm ready to use my, what am I trying to find? I'm trying to find the binding energy, right? So my photon energy, my base equation is the same as for the photoelectric effect. The photon energy shows up in 2 places. It's the binding energy that we have to overcome plus the kinetic energy. We used that before. So the binding energy is equal to the photon energy minus the kinetic energy. And I can do that here in my per mole units just as well as I could anything else. So this is now 11.9 megajoules per mole minus the 10.6 megajoules per mole. So that all gives me 1.3 megajoules per mole. And that tells me that's the binding energy for my hydrogen atom. Suppose I wanted 1 atom. That's how much energy it would take, 1.3 million joules, to pull the electron off of each and every one of the hydrogen atoms in a mole, right? So if I wanted to get to 1 atom, I could take that 1.3 million joules per mole and I could divide it by Avogadro's number. Then I would have how much for 1 single atom. Okay, you could do that if you care to, and just convince yourself that it has to make sense that way. So suppose I went to helium, right? I probably should have said a few words before I flipped the slide, but I did. So when I go to helium, now my atom has 2 electrons, right? So if I don't know anything about helium, there's 2 different possibilities. Both electrons could have the same binding energy, in which case I'll just see 1 peak in my spectrum. Or the 2 electrons in any given atom could have 2 different binding energies. There could be ones that are easy to take out and ones that are harder, right? That would give me 2 separate binding energies. The plot here is, again, a little bit strange, right? So on the y-axis, I have the number of electrons detected. On the x-axis, I have the binding energy. So I've converted into binding energies. Well, I haven't. I stole these figures from somewhere. But also notice that the binding energy is getting smaller from left to right. Okay, so that means that this side is held more tightly. This side is held loosely, let's say. If the binding energy gets to 0, that says the electron's not attached, right? So the fact that there's only 1 peak in here tells me that the 2 electrons in any helium atom appear to have the same binding energy. That's something we didn't know before this, if we were just starting out in this process, right? It could have been different from that. We also know the binding energy. It says it's 2.37. We just calculated for hydrogen that we got 1.3. So that says the helium atom holds on to its electrons more tightly than the hydrogen atom does. It's harder to knock an electron off of helium than it was for hydrogen. Okay, these are things we start to learn by looking at these kinds of spectra. Okay, suppose I hopped ahead some of the periodic table. I think the next one up is going to be neon. A neon atom, neon is atomic number 10, which means it's got a total of 10 electrons in it. Okay, and my spectrum looks like this. You'll notice there's a big region cut out here. That's because nothing happens in there. Okay, so there are 10 electrons altogether here. Think about this. First of all, I see I have 3 different peaks. All right, that means there are 3 different binding energies in any one neon atom. That means there have to be some different numbers of electrons that have the same binding energy, that are in the same energy level, we will come to say, okay? If I think about it, if I've done the experiment carefully, and the figures I've got here these are not real data, these are just sort of cartoon sketches of what the data might look like, to be totally honest. But if I look at them, I can see that down here I've got some electrons that are held very tightly, right? My binding energy down here looks like it's, I don't know, 83, 84, something like that. That's a lot bigger than we've seen before. Up here, I've got a peak that's around 2. That one is actually similar to the helium one we just saw. And then I've got another one, which is in between, okay? Suppose I want to think about why the peaks are different heights, because it's clear that this one over here is much taller than the others, right? The height of that peak, or perhaps a little better, the area under those peaks, should be related to how many electrons there were that had that binding energy, right? If I had more electrons that had a given binding energy, then there's that many more chances to knock one of those off, okay? So the taller peak should be indicative of there being more electrons in this loosely bound state than in the more tightly bound states. If I measure up the different areas under those things, or the heights, they're in a ratio that's roughly 1 to 1. Those 2 are obviously the same size. This one is about 3 times as big, okay? That says I have a total of 10 electrons, and if I want to take 10 things and put them in a 3 to 1 to 1 ratio, that says that down here I have 2 electrons, here I have 2 more electrons, and here I have 6 electrons that were in the energy levels that gave rise to those different peaks, okay? So that's how my 10 electrons are divvied up. I have 2 that are in a very tightly bound energy level, 6 that are in a very loosely bound energy level, and 2 that are in between. This tells me a lot about how the electrons in neon are arranged. Some of you, if you remember back to some things in high school chemistry and you remember learning about electron configurations, you might be kind of thinking, I know what this part is telling us. And so that is where we're headed. Okay, so let's take a look at a summary of what happens in the different experiments. Okay, so in the data here, I've got different plots, and I'll explain as we go what they look like. Okay, if you're reading through the slides, that one will help you make sense of what they look like. So here on my x-axis, I've got atomic numbers. So this is elements from hydrogen up through 18, it looks like. So that's argon there. Okay, so this is the first 3 rows of the periodic table is what's in my slide there. On the y-axis, I've got these binding energies still in this somewhat bizarre megajoules per mole unit, okay? Hydrogen, remember, had just one peak, so did helium. So the blue diamonds down here that you can't even really see where it is, these are the energies for those single peaks. Once I get past helium, I go to lithium, I guess, and at that point, I start having more than one peak show up, okay? That's the atomic number 3. That's the first element where there are 2 peaks. So now I get a blue diamond, and then I get a pink square underneath there, okay? You'll notice that the blue diamond starts at very small binding energy, and it quickly starts rising up. To the extent we can see them, we see as we go higher and higher atomic numbers, new peaks grow in, and they also start rising up. Vertical scale, y-axis scale for this one is 0 to 400, okay? Let's zoom in. Now we've zoomed in by a factor of 10. My y-axis scale now only goes up to 40, right? Still in the same units. Notice on this scale, I can see how quickly this starts swooping upwards, okay? And it goes off the scale of this quite readily. I can see that at atomic number 3, I get another peak growing in. The next one starts at 5. Then the next one starts out here at 11, it looks like, okay? And then subsequently, I get another one again at 13. And I could keep going if I went to higher atomic numbers. We'd keep seeing that happen. So each time a new peak grows in, it starts at a small binding energy, and it gradually starts climbing up in binding energy as we go to larger and larger atomic numbers. Let's look at how we could summarize those data for a few elements. This one, and again, I'm really bad about putting these energy labels on there, but on the y-axis, I have energy in the vertical direction going upward. My figure here is horribly not to scale, because if it was to scale, it's really hard to get all this on one thing, okay? So my energies are not scaled. My energies are shown in units of megajoules per mole. Effectively here, the negative numbers just means that when the energy reaches 0, that's where the electron would fall off of the atom, okay? So the absolute value of that, energy that's shown here is what I've been calling the binding energy. These are helium, neon, and argon, the first 3 elements in group 18, the so-called noble gases, okay? You'll notice that at the top of this, the most loosely bound electrons, okay, those are the only ones for helium, but the most loosely bound for neon and for argon, they're all reasonably close in binding energy. They're hanging out in the general vicinity of 2 in these units, right? As I go up in atomic number, though, you'll notice that down here in argon, I have some electrons that are held super tightly, right? 309 megajoules per mole it cost me to get those out of there. For neon, my strongest ones are 84, still a far cry from the 2 we started off with, right? You'll also notice there's a pattern here where I've got electrons occurring in groups of 2 and groups of 6, right? I get a 2, 2, 6, then here I get 2, 2, 6, and then I get another 2 and 6. That's what we refer to as shells. We talk about this as being the shell model for the atom, right? That says I fill up my first energy shell, and that's the one that helium has filled, where there are only 2 electrons total. At neon, I have filled up the first 2 shells, total of 8 electrons, total of 10 electrons rather, 2 in the inner shell and then 8 in the next one. When I get to argon, now I've got 2 and 8 again in the filled shells or subshells in that case, we'll eventually come to see. But this is experimentally shown, right? So what we're looking at here is all data we got from the experiment. We haven't made any kind of theory or model to explain this yet. We're going to do that next. But when we do that, we have to get a model that is consistent with these things, that says there will be energy levels that will hold 2 electrons and some other ones that will hold 6 electrons and so on. And be able to argue that it makes sense that their energies should shift as we go through the periodic table like they do here.